In this video, we discuss concavity and the second derivative test. Let's say f is a function that's differentiable on an open interval I. Then we say that the graph of f is concave upward if f prime is increasing on I. And if f prime is increasing, that means f double prime is positive. So we have f double prime, which is positive. Now, graphically, what that's going to correspond to is a graph that looks kind of like this. The entire graph lies above its tangent lines, but that's really not how I tend to think of it. I tend to think of it this way. The derivative on this side, the first derivative, is negative, right? So it's a very, very large magnitude negative slope here, and then it gets less and less negative until we get to the bottom, and then it has a zero slope. And then the slope starts to increase, and the slope is positive on this side. So f prime is negative on the left-hand side, 0 at the bottom, and then positive on the right. So if it goes from decreasing to 0 to increasing, or if you prefer, you can use positive and negative signs. It's going from negative values to 0 to positive values. And those negative values are very large negative, and they become less negative, and then they become 0. And then they become positive, and then they become increasingly positive and increasingly increasingly positive as you get over here. So essentially the tangent line is very, very steep on this side. So that derivative is increasing. So what we have is a second derivative, which is positive, and the graph roughly looks like this. Now, if the first derivative starts out positive, like it's on this side, so it's a very, very steep slope, and then the lines get less steep and less steep and less steep until we get a 0 slope at the top. And then they go from having a 0 slope to a negative slope, say -1/2, and then -1, and then eventually -2 and -5, and it just keeps getting larger and larger in magnitude, but increasingly negative. Our derivative values are going from a positive value to a 0 value to a negative value. Those derivatives are decreasing. In that case, the graph is concave down. So we've got f double prime is negative in that case. So if you see a graph and it looks like this, you know that the second derivative is positive. And if you see a graph that looks roughly like this, you know that the second derivative is negative. So we call this concave, this graph is concave downward on that interval, and this graph is concave upward on that interval. Now, a point of inflection is a point on the graph where f changes from concave upward to concave downward. So you might have a curve that looks roughly like this. So it's concave upward over here on this side, but then there's some point when that concavity switches from concave upward to concave downward. That point is called a point of inflection. Now, another requirement in our textbook is not just that the second derivative changes signs from concave upward to concave downward, or concave downward to concave upward, either way. But we also need the tangent line to be well defined. And I think I made a mistake here. It says f changes from concave upward to concave downward. Let's just say where the graph changes from, actually, I'm gonna define this a little differently. Concave upward to concave downward, or concave downward to concave upward. And the tangent line has to be well defined. Then we call that a point of inflection. So in other words, f double prime changes signs from positive to negative or negative to positive at a point of inflection. So I'll call that a point of inflection. All right. Now we can use these two pieces of information and the relationship between this graph and the second derivative to determine the intervals where our function is concave upward and concave downward. We can also use it to determine whether critical values correspond to relative minima or relative maxima. That is called the second derivative test. Now, we already know that with the first derivative test, if our first derivative changes from negative to 0 to positive, we've got a relative min. Or if our first derivative changes from positive to 0 to negative, then we've got a relative max at that point where the x value, or that point where the derivative is 0. Well, the second derivative test is very similar, but instead of looking at how f prime changes signs, we look at the sign of f double prime at that location. So let's say that f prime of c equals 0. So c is a critical point where the derivative is 0. So we're at a min, or we're at a flat spot on the graph. So the tangent line is horizontal. If f double prime exists on an open interval containing that x value, and f double prime is positive, then we know the graph is concave up and the derivative is 0. So we must be at the bottom. So f of c has to be a relative minimum. Now, if f prime of c is equal to 0 and f double prime is negative, well, we know the graph is concave downward and the derivative is 0. So we must be at a relative max. So that's the second derivative test. You could use the first derivative test instead if you prefer, but some people actually like doing the second derivative test. The nice thing about using the second derivative test is that you also have those intervals where that second derivative is positive and negative, and it can help you draw a better graph than like a more precise graph than the graph that you would get if you just looked at the sign of the first derivative on various intervals. So let's use the second derivative test to find some extrema, and let's find the intervals where a particular function, a particular function's graph is concave upward and concave downward. We can use this information with all of the information we studied in the previous section to determine the intervals where the function is increasing or decreasing, where the graph is concave upward, concave downward, where we have relative extrema, and then we put all those pieces together to graph our function by hand without using a calculator. Okay, so we've got a polynomial function, and we want to find the intervals where f is increasing or decreasing. So the first thing that we do is we compute the first derivative, and then we find the critical values of the function. So I have y equals this constant times this polynomial. So y prime is that constant times the derivative of the polynomial. And the derivative of -3 times x to the 5th can be found using the power rule. You bring the constant down, and then you bring the power down, and then you multiply by x to the 1 less power. So we're going to have the -3 times the 5 gives us a -15 out front, times x to the 5 minus 1, which is 4. Then we bring down the 40, and we multiply by the derivative of x cubed. So it's going to be 3, because we bring the power down. We multiply by x to the 1 less power. That's an x squared. And then we add the derivative of 135x. The derivative of constant times x is just the constant. So we've got this. Now, I think that all of these are actually divisible by 3. So we could simplify this a little bit if we wanted to. But I really don't know that it makes any of the calculations easier. Well, actually, let's factor out that 3. If we factor out a 3 from everything, we'll have 3 divided by 270 times -5x to the 5th plus 40x squared plus 3 goes into 13 4 times, and then it goes into 15 5 times. So that's what we have there. It looks like we've got an extra factor of 5 as well. So I'll divide that. 3 goes into 27 9 times. So this is going to be 1 divided by 90. And then we'll factor out a 5 as well. So -5 times x to the 4th would give us this -5x to the 4th. -5 times -8x squared would give us that that positive 40x squared. And -5 times -9 would give us that 45. So we've got this. And 5 goes into 90, 18 times? So we end up with -1/18 times x to the 4th minus 8x squared minus 9. So that's our y prime. And we want to factor that as much as possible in order to find the intervals where the function is increasing or decreasing. Again, I guess, hold on just a second, I'm sorry. We want to find the critical values of this function, and finding the critical values involves finding those x values where the derivative is 0. So let's write that down. So that involves computing y prime, setting y prime equal to 0 and solving for y, or excuse me, solving for x. So we have y prime equals 0 when this polynomial equals 0. And that negative 1/8 doesn't change anything. If negative 1/8 times this equals 0, it just means that polynomial equals 0. Now, one thing that I want you to notice is that that polynomial is quadratic in form. If I take x squared and I square it, I get x to the 4th. So this can be factored in the same way that a quadratic is traditionally factored. Just first times first has to be x to the 4th instead of an x squared. So I'm going to use an x squared here and an x squared there. And then I want to find two numbers that give me a product of -9 that have a sum of -8. Now, if the product is negative, that means the two numbers are going to have opposite signs. So we actually want two numbers that multiply to give us 9 that have a difference of 8. 1 and 9 will work if the 9 is negative. 1 plus -9 is -8. And 1 times -9 is -9. So this expression can be factored as x squared plus 1 times x squared minus 9. And that is the factored form of y prime, or at least excluding that extra constant value. So we can keep factoring. A difference of squares factors. A sum of squares does not factor. It factors in the complex numbers, but not the real numbers. A squared plus b squared factors to a plus b times a minus b. If a squared is x squared, a is x. Since b squared is 9, b is 3. So we're going to add 3 and subtract 3 there. And this will equal 0 in the real number system whenever this factor equals 0, which never happens. This factor equals 0, which is when x equals -3, or when this factor equals 0. So that means x equals -3 and x equals +3 are critical values of this function. Or critical numbers. Either way is fine. You can call it whatever you want.
Yes.
And then notice that since it's a polynomial, there are no critical values corresponding to y prime being undefined. So we'll say y prime is well-defined everywhere. So the only critical numbers that we have are these guys. Okay, so we found our critical numbers. Now, once you have your critical numbers, we want to create a sign chart for y prime. Now remember, y prime is actually the product of this -1/8 and that polynomial. So it's actually -1/8 times this, times this, times this. And we put, the way we do our sign analysis is we write our critical numbers on a number line. So we actually have 3 intervals of interest: -infinity to -3, -3 to 3, and then 3 to infinity. And then we say y prime is the product of -1/8, x squared plus 1, x minus 3, and x plus 3. Now, the only places where those factors change signs is potentially at these values. A -1/8 is always negative. It doesn't matter what interval we're on, it's negative. And x squared is always non-negative. It's always positive or possibly 0, but then we add 1 and it's definitely positive. So every interval that's positive. Then x minus 3 is positive when x is greater than 3. Say, like, if you plugged in 5, you would get a 2. And if it's going to be negative whenever x is less than 3. If you substitute 0 here, you get 0 minus 3, which is negative. If you substitute -4 here, -4 minus 3 is -7, which is negative. But we can see that this is going to be positive when x is greater than 3. And this one's positive when x is greater than -3. So we'll have a positive here and here, and then it'll be negative on this interval. If you want, you can always plug in an x value from each of these intervals to these functions. Whatever the sign is for that test value in each of the intervals is the sign of that factor on that interval. So we say, okay, we're creating a sign chart. Y prime is this times this times this times this. And if y prime is the product of those, we know negatives cancel in pairs. A negative times a negative is a positive, times a positive is a positive, and a positive times a negative is a negative. The function is negative on that interval, or y prime is negative there. And then we have a negative and a positive and a negative and a positive. Since the negatives cancel in pairs, y prime is positive on that interval. And then we have a negative times a positive times a positive times a positive, which is negative. So that tells us where our function is increasing and where it's decreasing. We say y equals f of x is increasing on this interval and decreasing on the other two intervals, on negative infinity to negative 3 and 3 to infinity. Now, graphically, we know that those x values correspond to a zero derivative. So we know that the function has a zero slope at those x values. So we can also use the first derivative test here. We say, well, the function is decreasing, then it has a zero slope, and then it's increasing. So x equals negative 3 must correspond to a relative minimum. Near x equals 3, the function is increasing, then it has a zero slope, and then it's decreasing. So x equals 3 must correspond to a relative maximum. So using the first derivative test, we can say that since f prime changes from negative to positive at x equals negative 3, f of negative 3 is a relative min. And I don't know what that value is, but I can just plug in x equals negative 3 to the original function and evaluate it to find the y value. And since f prime changes from positive to negative at x equals positive 3, then f of 3 is a relative min, or excuse me, relative max. And I don't know what that value is, but again, I could just plug that x value into the original function and find the corresponding y value. This is called the first derivative test, where we look at how f prime changes. If f prime changes signs, then we either get a relative min or a relative max, and depending on how it changes signs, that's how we know the difference between the relative min and relative max. So we know where the function is increasing, we know where the function is decreasing, and we use the first derivative test to classify those critical values as corresponding to either relative mins or maxes. So we did this part here. Now we also want to do the same thing, or create a sign chart again, excuse me. But this time we're going to be using the second derivative rather than the first derivative to determine the intervals where our graph is concave upward or concave downward. So we know that y prime is equal to this function. In order to find the intervals where the function is concave upward, or the graph of the function is concave upward or concave downward, we need to take the derivative again and find out where that second derivative is either positive or negative. So we'll do that. So y double prime is the derivative with respect to x of that negative 1/18 times this x to the 4th minus 8x squared minus 9. And the derivative of x to the 4th is 4 times x cubed. Then we take the derivative of 8x squared, you bring the negative 8 down and multiply by the derivative of x squared, which is 2x. And the derivative of negative 9 is 0. So we end up with this. We can factor out a 4 if we want to. And an x if we want to. And we say 4x times x squared is 4x cubed. And 4x times a negative 4 is that negative 16x. That 4 has a factor of 2 in common with the 18, so we can divide out the 2 there and there. The negative 9, or 2 divided by 9 times x times this x squared minus 4. That's our y double prime. Now, in order to find the intervals where y double prime is positive or negative, we need to find the x values where y double prime is 0. So we set y double prime equal to 0 and solve for x. Now, x squared minus 4 is a difference of squares, so we can factor that. factored form of a squared minus b squared is a plus b times a minus b. A in this case is x. Since b squared is 4, b in this case is 2. So we add 2 and subtract 2. So this times this equals 0. So that means either x equals 0, that's when this is 0, or x equals -2, or x equals +2. These are not critical values, but they're like critical values in that we're going to place these values on the number line and look at the sign of y double prime on the intervals determined by these x values. So we've got this. And of course, you want to put the numbers in order, -2, then 0, then 2. And we're interested in the sign of y double prime. Now, y double prime is this -2/9 times x plus 2 times x minus 2. A -2/9 is always negative. Doesn't matter what x is. We always get a negative there. Now, x is, of course, positive when x is positive. So x is positive on these two intervals. X is negative on those two intervals. And x plus 2 is going to be positive whenever x is greater than -2. So it'll be positive here and here and here. And if you're not sure, you can always pick an x value on each interval and plug it into that factor. And that will give you the sign of that factor on that interval. So if I wanted to, I could say x equals -1 is on this interval. -1 plus 2 is +1. So we know that that's going to be positive the whole time there. But the point is, the only place where y double prime changes signs is at these values. So when you pick a test point, the value of the function or value of that factor at that test point on the interval is the sign, or it gives you the sign of that factor on the entire interval. Now, on the interval from -∞ to -2, x plus 2 is going to be negative. You could pick a test value like -3. -3 plus 2 is -1. That's a negative number, so we'd write a negative sign there. Now, x minus 2 is positive when x is greater than 2. So if I plug in 4, 4 minus 2 is +2, so I get positive. Now, every other interval, when x is less than 2, we're going to get a negative number. And you could choose test values, -3, -1, and 1. Plug those in there, you're going to get negative values every time. Now, y double prime is the product of these. So it's a negative times a negative times a negative times a negative, which is positive. This is a negative times a negative, which is positive, and a positive times a negative, which is negative. So we're going to have the negatives canceling in pairs. We're still going to have one negative left. These two negatives cancel in pairs, so we're going to have a positive, and then we have a negative here. So this is a sign chart. It's interesting, though. This is for y double prime, not y prime. So this tells us where the graph is concave upward or concave downward. We say the graph of f is concave upward when y double prime is positive. Or in other words, on these intervals. It's not equivalent. Sorry, shouldn't write that double-headed arrow. So the graph is concave upward on -∞ to -2 and 0 to 2. And the graph of f is concave downward. I'm not going to write the whole sentence this time. I'm just going to write concave downward when f double prime is negative or y double prime is negative. So on this interval, -2 to 0 and 2 to infinity. Now, the points of inflection of the function are those points where the graph changes from concave upward to concave downward or concave downward to concave upward, or in other words, where y double prime changes signs. As long as that point is a point on the graph and the derivative is well defined there. So the points of inflection are actually given by this x coordinate and the corresponding y value, and this x coordinate, and this x coordinate, 0, and the corresponding y value, and this x coordinate and the corresponding y value. So we actually got 3 of them because our graph is concave upward here, concave downward here, concave upward here, and concave downward here. And there's going to be a point where it changes. And that point where it changes from concave upward to concave downward, or concave downward to concave upward, or concave upward to concave downward, corresponds to the ordered pair given by these three x values and their corresponding y values. So that's what we've got. We wanted to know where the graph is concave upward and concave downward. We know that now. And we could have used, if we wanted to, the second derivative test to determine the relative extrema. We didn't, but we could have. Now, remember how the second derivative test works. It says, if we're at a critical point and the second derivative is positive there, the graph is concave up. So we must have a relative min. If we're at a critical point and the second derivative is negative, the graph is concave down. So we must be, and since the derivative is 0, must be at the top. We must be at a relative max. So we already know that x equals -3 and x equals +3 correspond to a relative min and relative max from the first derivative test. But we could just as easily determine whether x equals -3 and x equals +3 correspond to relative minima or maxima by using the second derivative test. So let's use the second derivative test to confirm what we found using the first derivative test. So the second derivative test says, take each of your critical values and evaluate the second derivative at that critical value. So we have -1/3, or excuse me, f double prime evaluated at -3 is -2/9 times x plus 3, excuse me, x plus 2 times x minus 2, but we're evaluating at x equals -3. So we're going to have -2/9 times -3. -3 plus 2 is -1. -3 minus 2 is -5. So we're going to have, looks like 15 times 2, which is 30 divided by 9. So we get 10/3 for our value there. And since 10/3 is positive, we know the graph is concave upward, and we know that the derivative is 0. So that means f of -3 is a relative min. And if you want to find the y value there, you can. It was 1/270 times -3 times x to the 5th plus 40 times x cubed plus 135 times x. So I evaluate this at x equals -3. And I think I'm just going to use a calculator for that. It's just arithmetic. That value is the relative minimum value. And then the other critical point with x equals +3. So we evaluate f double prime at that other critical point or critical value. So we've got -2/9 times x plus 2 times x minus 2. And we're evaluating at x equals +3. So we've got -2/9 times 3 times 3 plus 2, which is 5, times 3 minus 2, which is 1. And so we end up with -30 divided by 9. We divide the numerator and denominator by 3, we get -10 divided by 3. So the second derivative is negative there. So that means our graph is concave downward. And this is a critical value corresponding to a 0 derivative. So we're at the top there. The graph is concave downward and we're at the top. So that means that f of 3 is a relative max. And if we wanted to find that by hand, we would just do this, evaluate the function at 3. But that's a little tedious. I think I'm going to use a calculator for that. We'll plug in 3 here and here and here and here, and then we'll find out what that number is. Now, if we've done everything correctly, we should get the same answers using the second derivative test as we do in the first derivative test. The claim is that from the second derivative test, the f of -3 is a relative min. Well, when we did our sign chart for the first derivative, we said by the first derivative test, f of -3 is a relative min. Using the second derivative test, we found that f of 3 was a relative max. Using the first derivative test, we found that f of 3 is a relative max. So we know we're doing this correctly. So we've got our relative extrema. We know the intervals where our function is increasing and decreasing, concave upward and concave downward. We can put all of those pieces together to graph the function now. But it is also helpful to have the corresponding y values. So I think what I'm going to do is I'm going to use a calculator real quick to evaluate the function at these points. And we also want the value of the function at these points. And then we'll use those to graph our function. We'll graph our function by hand, and then we'll confirm that our graph is correct using Desmos.com. Okay, so I'm just using Desmos as a calculator now to find f of 3 and f of -3. F of 3 turns out to be 2.8, and f of -3 equals -2.8. And then at our points of inflection, we had f of 2, f of -2, and f of 0. F of 2 turns out to be 247 divided by 135. I don't know what that is, but I can find a decimal approximation by pressing that number or pressing that button on the side, excuse me. So that's approximately 1.829 or 1.8296. And at -2, because of the symmetry, we end up with the same value but negative. So -270 or 47 divided by 135. So that's approximately -1.8296. And our function value at 0 is just 0 because x equals, or x is a factor. Okay, now I could just graph the function and the points now using the calculator, but I don't want to do that. I want to see if I can graph it on paper and then see if the graph on paper looks like the graph of the function online. So let's do that.